Today we're adding an extra dimension to the method of least squares estimation. In the least squares solutions we've considered so far, we assume that all observations are equally important to solve the problem. In reality, it is unlikely that all observations have the same importance. For example, in our example on sea level rise, observations of centuries ago may be poorer in quality than modern new observations. To account for these differences, we will now introduce the method of least squares estimation, but in a weighted sense. This is the summary we gave on the standard least squares estimation solution. We formulated our y is ax problem and came to the least squares estimate x hat. Essentially what we did was to minimize the difference between our actual measurements, which are the red crosses over here, and the linear model which we assume to be applicable, which is the green dashed line over here. These differences, or the residuals, are indicated by the little vertical blue lines, and we call these the least squares estimates of residuals, or E hat. Mathematically, we obtain this solution by minimizing the sum of the squared residuals, which then yields the least squares estimate. So, if we would know that some measurements are better than others, the standard least squares method will not be optimal, since it doesn't consider this information at all. In fact, what we want to do is to give observations different weights. A higher weight means that that observation will have more influence in the estimation. To introduce the concept of weighted least squares, let's start with an intuitive approach. Remember the canal width experiment. Here we measured the width of the canal in different ways. And I want to focus on the direct measurements. So I'm referring to those measurements where the width is measured directly without any further computations. We see two examples here on this slide, the direct measurement with a rope or the direct measurements with an electronic distance measurement. Let's suppose that we have collected 3 of such direct measurements and look at the model of observation equations. This could be a suitable functional model. We see 3 observations, y1, y2, and y3. We see the unknown width of the canal, x, and the vector of errors or residues, e. Now, let us suppose that observation y1 is of better quality than the other 2. This means that it should get a more weight, a higher weight. We don't know exactly how much more, but for now we assume that this observation should have twice the weight of the other 2 observations. How do we do that? The standard least squares approach here in the lower right, down here, does not allow any weights. So first I would like to fix this problem in an intuitive way. If we want to give the first observation a double weight, what we could do is simply copy that particular observation in the system of observation equations. Here we see that observation y1 is now listed twice in the observation vector. So the same number is listed 2 times. Let's work out this equation and see what the effect is. With this system of observation equations, we find the least squares estimate by multiplying the design matrix, A, so that means A transposed times A, taking the inverse of that, indicated by the -1 exponent, and multiplying that result with the sum of all observations. In this case, this is easy, as you can see. And it yields this final equation. So let's see what we've got here. Our first observation, y1, now appears with a factor 2 in front of it. The equation is in fact a weighted average of the 3 observations. Now, let's see if there's a more elegant way to arrive at the same result. We can arrive at the same result by using a weight matrix, W. This weight matrix expresses the relative weights between the observations, and it could even deal with correlations between observations. But we're not going this far at this time. The weight matrix is a square matrix with the same number of rows and columns. This number has to be equal to the amount of observations. In our example, we had 3 observations, So therefore, the size of the weight matrix is 3 by 3. Also, in our example, we assume that the first measurement should have twice the weight of the other two. So therefore, the weight matrix looks like this. We see that the weight of observation y1 is equal to 2, while the weights of the other two observations are equal to 1. The fact that the off-diagonal elements in this matrix are equal to 0 means that there is no correlation between the observations. Now let's see where we should introduce this weight matrix in the equation for the least squares estimate. For now, I will simply give you the answer to this question and work out a proof for this answer in a different video. If the solution for the standard or unweighted least squares estimate is this equation, then the solution for the weighted least squares estimate is this equation down here. Here we see that the weight matrix W appears twice. Since we introduced this without proof for now, let's see whether it works for our example of the canal width estimation. We start with the equation for the weighted least squares estimate x hat. Since we have 3 measurements, the A matrix is 3 by 1. It's a matrix of ones. And the weight matrix W assigns a double weight for the first observation. So if you work it out, it looks like this. Working this set of equations out in 2 steps yields the results that you see down here. If we compare this with the result of our intuitive approach, where we simply copied observation number y1, we see here that these results are identical. This means that we now have expanded our repertoire of least squares estimation from the unweighted form to the weighted form. If we would insert a unit matrix as a weight matrix, which means that the W matrix is a diagonal matrix with ones on the diagonal, we see that the unweighted least squares estimator can actually be considered to be a special case of the weighted least squares estimator. It is a special case because all weights in the weighted matrix are then equal. For this reason, it is okay if you would forget the first equation, the upper one over here, and only remember the one with the weighted observations down here. So, in this video we discussed weighted least squares estimation. This weighted form enables us to add information on the importance of specific observations in the estimation process. We can do this by introducing a weight matrix. We discussed weighted least squares in an intuitive way and simply postulated the required equations. In further videos we will show how we arrive at these equations and how we can find the weights that we need in the weight matrix.